You know, corrosion, it's this silent, relentless enemy that costs our global economy something like $2.5 trillion every single year. It's what brings down bridges, it's what bursts pipelines, and it's what turns shiny new cars into piles of rust. Now, to fight it, to actually beat it, we first have to understand it. We have to get into its science. So let's dive right into the core theory that makes all corrosion protection, especially cathodic protection, possible.
We're going to build this thing from the ground up. First up, we'll take apart that tiny little electrochemical engine that causes all the trouble, the corrosion cell. Then, we'll get into what actually powers it and what environmental triggers kick the whole thing off. After that, we'll figure out how to measure the destruction it leaves behind. And finally, we'll explore what slows it down and all the different shapes and forms it can take. All right, let's get started.
You have to realize every single spot of rust you've ever seen, every pit in a pipeline, it all starts with this one single concept: the basic corrosion cell. Think of it like a tiny little engine of destruction, and it's got 4 essential parts that all have to be there for corrosion to even get started.
And this diagram right here, this is the heart of it all. The best way to think about it is like a tiny, destructive little battery. You've got 4 key players on the field: an anode, which is where the metal actually dissolves; a cathode, which is the part that stays protected; an electrolyte, which is kind of the conductive soup they both sit in; and a metallic path for the electricity to flow. Now here is the most important takeaway of all. If you can remove any one of these 4 components, you break the circuit, and corrosion just grinds to a halt. That right there is the fundamental principle behind almost all corrosion control.
So, let's start with the anode. This is where the action happens. And, this is where the damage happens. It's the part of the metal that is actively sacrificing itself. It literally gives up tiny particles of itself, we call them ions, into the electrolyte. And in doing so, it releases electrons. This chemical reaction has a name. It's called oxidation. And oxidation is the very definition of corrosion. So all those electrons that the anode just released, well, they have to go somewhere, right? They travel along that metallic path to our second component, the cathode. Now, the cathode is the protected site in this little circuit. It's the good guy, so to speak. It accepts and consumes the electrons in a different reaction called reduction. The key here is no metal is lost at the cathode. In fact, the cathode is what the anode is corroding to protect. Okay, so we've got electrons flowing from the anode to the cathode through the metal. But what about those metal ions that dissolved from the anode? They need to complete the circuit too, and that's the job of the electrolyte. This isn't like a wire, it's any substance that has ions in it that can conduct electricity. Think soil, seawater, or even the moisture that's trapped in concrete. It's basically the highway for ions, connecting the anode and cathode and letting that whole electrochemical reaction keep on running.
And the final piece of our puzzle is the metallic path. This is the physical connection, the wire that lets the electrons actually get from the anode to the cathode. Now, it could be a literal wire, but more often than not, it's the metal structure itself. You know, the body of a car, the girder of a bridge, or the wall of a pipeline. So once you have all 4 of these things in place, anode, cathode, electrolyte, and metallic path, you've got yourself a complete, current-flowing, metal-eating circuit.
So what makes this circuit run in the first place? What's the driving force? Well, it all comes down to something called electrical potential. The easiest way to think about it is like water pressure. The bigger the difference in electrochemical potential between 2 different metals, the more pressure there is pushing that corrosion to happen. And to understand that pressure, we start with this table right here, the standard EMF series. Think of it as a theoretical ranking, a league table, of how willingly different metals give up their electrons, but under perfect, sterile lab conditions. It ranks them from the most noble or stable, like gold, way up at the top, down to the most active or reactive, like magnesium at the very bottom. And here's the key. The more negative that voltage number is, the greater that metal's natural tendency is to become the anode and corrode when you connect it to any metal above it on this list. But here's the thing. We don't work in a lab, do we? The real world is messy. It's wet, it's dirty. And that's why for us, we have the practical galvanic series. It takes the same idea, but it ranks metals based on their actual measured potentials in a specific real-world electrolyte, like seawater. For any field technician, this is the guide that really matters.
Now, this is where this whole concept becomes an incredibly powerful tool for predicting what's going to happen. This is a practical galvanic series for seawater. And here's how it works. You can pick any two metals on this list, and the one with the more negative potential, so the one that's higher up on the chart, will always become the anode and corrode if you connect them electrically in seawater. So for example, if you connect clean steel, which is sitting around minus 0.5 volts, to copper up minus 0.2 volts, guess what happens? The steel will rust away to protect the copper. And that, my friends, is the basis of galvanic corrosion.
Okay, so those galvanic series tables are awesome for a specific environment, like seawater. But what if your pipeline is buried in soil that has a totally different ion concentration? Or what if it's operating at a higher temperature? We need a way to adjust those standard lab values for real-world conditions. And that is the power of the Nernst equation. It's the formula that lets us fine-tune our theoretical predictions for the messy, complicated reality we find out in the field.
Now don't let all the symbols scare you. Let's just break this down piece by piece. The E on the left, that's what we're trying to find, the actual, real-world electrode potential. E0 or E0 is our starting point. That's the standard potential we pull from a reference table like the EMF series. The rest of this equation is basically a big correction factor. R is a constant, and T is the absolute temperature. That right there tells us that temperature directly affects potential. N is the number of electrons being transferred in the reaction, basically the metal's valence. F is just another constant, Faraday's constant. And that last part, with the A values, that accounts for the concentration or activity of the ions in whatever solution we're in. So in short, the equation takes a lab value and then it systematically adjusts it for the real-world temperature and chemistry.
So how would a corrosion tech actually use this? Let's walk through it. Step 1, you'd look up the standard potential for zinc, which is minus 0.763 volts. Step 2, you'd figure out how many electrons zinc gives up when it corrodes, which is 2. Step 3, you'd measure the concentration of zinc ions in your specific electrolyte. Let's just say it's a 0.01 molar solution for this example. And finally, step 4, you just plug all those values, the standard potential, the number of electrons, the temperature, the concentration, into the Nernst equation to calculate a really precise real-world potential for zinc in that specific environment.
So it's not always about connecting two different types of metal together. The environment itself is an expert at creating corrosion cells, even on a single uniform piece of metal. Little variations in temperature, stress, and chemistry can create thousands of tiny anodes and cathodes all over a structure.
Take temperature, for example. Just a simple difference in heat across the very same piece of metal is enough to create a corrosion cell. As a general rule, the hotter area becomes the anode and starts to corrode. The diagram shows a hot pipe coming right out of a compressor station. Well, that hot section becomes anodic to the cooler pipe further downstream. The exact same thing happens in a well casing, where the warmer, shallower part corrodes to protect the cooler, deeper section below.
You know, the way we actually manufacture metal parts can also bake corrosion problems right in from the start. When we alloy different metals together, or bend a pipe, or weld two pieces of steel, we create these areas of really high internal stress. Think of it like a tightly wound spring. It's just storing energy. These high-energy, stressed-out zones have a much greater tendency to become anodic, and they'll corrode much more easily than the less stressed areas right next to them.
But you know, one of the most common and sneakiest environmental triggers is something called a concentration cell. Now, in this case, the metal itself is perfectly uniform. The problem is that the electrolyte touching it isn't. A simple difference in the concentration of some chemical, like oxygen or salt, from one spot to another is all it takes to create a really powerful anode and cathode.
Let's look at the most common type, an oxygen concentration cell. The rule here is simple. The area with less oxygen becomes the anode and corrodes. This is exactly why a crevice, which is starved of oxygen, will start to rust first. A perfect real-world example is a pipe that's buried under pavement. The section directly under the pavement just can't get as much oxygen from the air as the section in the open soil next to it. So what happens? The oxygen-starved section under the pavement becomes the anode, and it starts to corrode away.
And this same logic applies just about everywhere. If you have a pipeline that passes from sandy, well-aerated soil into a dense, oxygen-poor clay, the section in the clay becomes the anode. Or, if a section of pipe is exposed to higher salt concentrations from road de-icing in the winter, that salty section will become anodic to the rest of the pipe.
All right, so we know what causes corrosion, and we know where it happens. But the big question is, how fast is it happening? How can we actually quantify the damage? For that, we need to turn to the laws of electrochemistry and some pretty essential field tools.
This brings us to one of the most important principles in our entire field, Faraday's law.
This is not just some abstract formula, okay? This is the fundamental law that gives us a direct, predictable, mathematical link between that invisible flow of electricity and the very real physical loss of metal. It means that if you can measure the corrosion current, Faraday's law lets you calculate exactly how much weight in metal is being lost over any period of time.
So let's look at the components. W is the weight of metal lost. That's what we want to find. This weight is directly proportional to three things. M, which is the atomic weight of the specific metal we're dealing with. I, the corrosion current flowing in amperes. And T, the time in seconds that the current is flowing. The bottom part of the equation just tells us it's inversely proportional to N, the number of electrons the metal transfers, and F, that Faraday's constant again. It's a really beautiful direct relationship. More current and more time simply equals more metal lost.
Now, the real power of Faraday's law is that it lets us pre-calculate this cheat sheet of electrochemical equivalence. And this table is incredibly useful for a corrosion engineer. It tells you, for example, that if you measure 1 amp of corrosion current on a steel pipeline, you know for a fact that you are losing exactly 9.13 kilograms, that's about 20 pounds, of steel every single year. This lets us translate an electrical reading from a multimeter directly into a rate of physical damage, which helps us predict when a repair or a replacement might be needed. But to make those electrical measurements out in the field, we need a stable, reliable reference point, right? You can't just stick one probe of your voltmeter onto a pipe and the other one into the dirt because the soil's potential is changing all the time. That's where this guy comes in, the copper-copper sulfate electrode, or CSE. It contains a specific chemical solution that gives it a constant, known potential. So by measuring the voltage difference between our pipeline and this stable reference, we can get an accurate, repeatable reading of the pipeline's structure-to-soil potential. Now here's an interesting thing. Corrosion doesn't just run wild at its maximum theoretical rate. The process itself actually creates a kind of back pressure, or resistance that naturally slows things down. This whole phenomenon is called polarization, and understanding it is absolutely critical for corrosion control.
Okay, let's break down this Evans diagram, because it's a really powerful way to see what's happening. The top red line, that's the natural or open circuit potential of the cathode, and the bottom blue line is the natural potential of the anode. Now, in theory, the voltage difference between them should be huge. But as soon as you connect them and current starts to flow, something happens. Their potentials start to shift or polarize toward each other. The point where they finally meet, right in the middle, that's the actual mixed potential you would measure on the corroding structure. And here's the most important part. If you look straight down from that intersection point to the horizontal axis, it tells you the real-world corrosion current, labeled here as I-core. The entire goal of corrosion control is to manipulate these lines to make that I-core value as small as humanly possible.
So why does this slowdown even happen? Well, there are two main types of polarization. The first is activation polarization. Just think of it like a traffic jam right at the toll booth. There's a bottleneck in the electrochemical reaction itself, like transferring the charge at the surface is just really slow. The second type is concentration polarization. In this case, the toll booth is working fine, but the road leading up to it is empty. The reaction is literally being starved for raw materials, like maybe not enough oxygen can get to the cathode, or the products are piling up and clogging the exit. Either way, the whole process slows way down.
And of course, lots of things in the environment can affect how much polarization happens, basically controlling the speed dial of corrosion. Higher temperatures or a faster flow of water, for instance, can deliver reactants more quickly and reduce that concentration polarization, which speeds up corrosion. The density of the current and the concentration of ions in the electrolyte, they also play a huge role in determining what that final corrosion rate will be.
Now, one of the most critical factors of all is the ratio of the cathode area to the anode area. And the point on this slide is absolutely vital. A small anode connected to a large cathode is the absolute worst-case scenario you can have. Imagine a tiny little scratch or defect, we call it a holiday, in a pipeline's protective coating. That tiny exposed spot of steel becomes the anode, while the entire rest of the huge, coated, protected pipe can act as the cathode. All of the corrosion energy gets focused on that one tiny pinprick. This creates an incredibly high current density, and that leads to rapid, deep pitting that can punch a hole right through the pipe wall in no time flat. It's incredibly dangerous.
Okay, for our final section, let's move from the theory to what we can actually see. Corrosion doesn't always look the same. Depending on the metal, the environment, and the specific mechanism at play, it can show up in several very distinct forms.
Depending on the conditions, this attack can take many forms. You might see a uniform attack, where the metal loss is just spread evenly across a big surface. Or you could see galvanic corrosion, where two different metals are touching. Pitting, which we just talked about, is especially nasty because it creates those deep, localized holes. Crevice corrosion loves to hide in tight gaps. Intergranular attack actually follows the grain boundaries inside the metal's crystal structure, and environmental cracking is a really dangerous combination of stress and a specific corrosive environment that can cause a sudden, catastrophic failure.
And this brings us to a final and very critical warning about fighting corrosion. The main technique we use, called cathodic protection, involves making our structure more electrically negative to stop it from being an anode. But it turns out we can go too far. As this quote from the NACE manual warns, if we apply an excessive negative voltage, especially to high-strength steels, we can cause a side reaction that generates hydrogen atoms right on the steel's surface. These tiny little atoms can actually seep into the metal and make it brittle. It's a dangerous phenomenon called hydrogen embrittlement. It's a classic case of the cure potentially causing another, even worse disease if it's not applied correctly.
So there we have it. We've deconstructed the engine of corrosion. We understand its 4 essential parts, the electrical forces that drive it, the environmental triggers that set it off, and the different forms of attack it can take. We have, for all intents and purposes, met the enemy. So the question now becomes, how do we use all this knowledge to fight back? How can we manipulate this electrochemical cell to our advantage, slow it down, or even reverse it to protect our structures? Well, that is the science of cathodic protection, and that's exactly what we're going to cover next time.
All right, welcome. We're going to do a deep dive into the fundamental principles of cathodic protection. We're basing this whole explainer on the NACE International CP2 Technician course material, so we can get a really clear, structured understanding of how we stop that inevitable process of corrosion. Okay, so here's our game plan. We're going to start with the problem itself. What exactly is a corrosion cell? From there, we'll build up to the solution, cathodic protection, and we'll look at how it's applied, what kind of real-world things affect it, and, how we actually measure if it's working. So before we can even think about protecting a pipeline or a ship's hull, we've got to get our heads around what's happening on an almost invisible, microscopic level. It all kicks off with something called the corrosion cell. At its very core, corrosion is an electrochemical reaction. The best way to think about it is like a tiny, unwanted battery that's literally eating away at your metal. And just like any battery you'd buy at the store, it needs 4 key things to get going. And this picture gives us a perfect look at those 4 parts, all happening right here on this pipe. You've got the anode, that's the spot where metal is actively being lost, it's dissolving. Then you have the cathode, which is the other half of the reaction. For this to work, you need an electrolyte, like damp soil, which lets ions travel between them. And finally, you need a metallic path, the pipe itself, to complete the electrical circuit. Now, here's the kicker. If you take away just one of these 4 components, the whole corrosion process grinds to a halt. And that's the principle we're about to explain. Now that we understand the problem is basically a tiny electrical circuit, well, the solution becomes pretty clear. We can fight electricity with more electricity. This is the whole idea behind cathodic protection, or CP for short. Take a look here. On the left, you see the natural state of things. Current flows from the anode to the cathode, and that anode corrodes away. Simple as that. But on the right, you see what happens when we apply CP. We introduce an external current that's stronger than the natural corrosion current, and we force it to flow to the entire surface of the pipe. This basically overwhelms all those little local anodic sites and turns them into cathodes. And if you have no anodes, you have no metal loss. The corrosion is stopped cold. So this effect, the change we're creating by applying that current, has a name. It's called polarization. We are literally changing the electrical potential of the structure we're trying to protect. This isn't just some side effect, it's the entire goal of the process. We are actively shifting the structure's voltage to shut down that corrosion reaction. Now this is really cool. This Evans diagram gives us a visual for what's happening. You see, every structure has a natural corrosion potential, which is labeled here as ECOR. By applying our cathodic protection current, that's ICP, we are physically forcing that potential down, making it more negative, until it reaches a new protected potential, ECP. We're essentially moving it out of the electrochemical danger zone. And this doesn't happen all at once across the whole surface. It's more of a step-by-step process. I want you to think of it like you're flooding a valley with water. The lowest points, which in our case are the most active, most corrosion-prone spots, they get covered with that protective current first. Then, as we keep applying more current, we cover more and more of the landscape until the entire structure is safely underwater, so to speak. Okay, so let's step away from the clean lines of the theory and get into the messiness of the real world. Because out in the field, there are a bunch of environmental factors that can dramatically change how much current we actually need to get the job done. So here's a crucial point. The amount of current you need is directly tied to the amount of exposed metal surface area. Just look at this calculation for a bare steel pipe. It needs a whopping 15.7 amps of current. But now, what if we coat that same pipe? And that coating is 95% perfect, leaving only 5% of the metal exposed at little defects. Well, the current needed just plummets to less than 1 amp. This is exactly why coatings are always our first line of defense against corrosion. The chemistry of the soil or water also matters a ton. As you can see here, a structure that's in a more acidic environment, that means a low pH, is going to require significantly more protective current than one in a neutral or alkaline environment. To put it simply, acidic soil is just more aggressive towards metal. Temperature also plays a huge role. You can think of heat as energy, and that energy just speeds up all the chemical reactions, including the ones involved in corrosion. So it's a pretty direct relationship. As the temperature of the environment goes up, so does the amount of current we need to pump in to counteract that faster corrosion rate. Next on the list is oxygen. Oxygen is like fuel for the cathodic side of the corrosion reaction. So if you have a pipeline buried in loose, sandy, or gravelly soil that lets a lot of air in, it's going to be exposed to more oxygen. That means it will require more protective current than a pipe buried deep in dense, oxygen-starved clay. And finally, we have to consider movement. If the electrolyte is flowing past the structure, think of seawater moving past a ship's hull, it's constantly bringing a fresh supply of reactants, like oxygen, right to the metal's surface. This constant resupply speeds up the corrosion reaction, which in turn increases our demand for protective current to overcome it. Okay, so we've designed our system, we're applying current, but how in the world do we know if it's actually working? We can't just eyeball it and hope for the best. For that, we rely on internationally recognized, field-tested standards and criteria. For steel and cast iron, the NACE International Standard SP0169 gives us our main benchmarks. The 3 most common criteria are a specific voltage potential, a minimum amount of voltage shift, and a third one that's based on historical corrosion rates. Let's really focus on those first 2, because they're the ones you'll see most often. This number right here, negative 850 millivolts, is probably the most widely used criterion in the entire industry. And that CSE is critical. It stands for copper/copper sulfite electrode, which is a type of reference electrode. It's essential because it gives us a stable, repeatable electrochemical baseline to measure against out in the field. Without that stable reference, our voltage readings would be all over the place and pretty much meaningless. So why that specific number, negative 850? Well, tons of lab research and fieldwork have shown that the most active, most aggressive corrosion sites on a piece of steel have a natural potential of right around negative 850 millivolts. So the logic is, if we can polarize the entire structure to be more negative than that value, we've effectively shut down every single little corrosion site on it. But there's a catch. When we go to measure our pipe's potential, the very current that we're applying for protection can actually create an error in our reading. This error is called the IR drop. Think of it as a voltage drop happening in the soil between our meter and the pipe, not on the pipe surface itself. To get a true, accurate measurement, we have to find a way to eliminate it. The way we do this is with a clever technique called an instant off reading. As you can see in this depolarization curve, we use a special switch to momentarily turn off the cathodic protection current. The IR drop, that error, disappears instantly, but the true polarization on the pipe surface takes some time to decay. The measurement we take in that split second right after the current is shut off is our true IR-free potential. That's the number we compare against our negative 850 millivolt criterion. Okay, to wrap things up, let's look at a slightly more advanced field technique and touch on how these ideas might change when we're dealing with materials other than just steel. This slide shows a really powerful technique called an E-log eye test. It's used to figure out precisely how much current you need. What a technician does is slowly increase the CP current, and at each step, they take an instant off potential reading. They then plot those readings on a semi-log graph, like the one on the right. This creates a straight line section we call the Tafel slope, which shows the pure polarization behavior. And the breakpoint, the spot where the data veers away from that straight line, right here at 13.0 amps, that tells us the exact current we need for complete protection. And this really leaves us with a final thought to chew on. A truly effective cathodic protection design is never, ever a one-size-fits-all solution. It's always a direct and calculated response to the specific, unique electrochemical environment that the structure lives in. The temperature, the oxygen, the pH, the movement, every single factor we've talked about changes the equation, and it demands a custom-tailored solution to stop corrosion dead in its tracks.
All right, let's get into it. Today, we're essentially becoming corrosion detectives. Our case, to figure out if a cathodic protection system, the thing that uses a tiny electrical current to stop pipes from rusting, is actually doing its job. Think of this as your field guide for a real-world investigation, how to gather the right clues, how to spot the red herrings, and ultimately, how to crack the case of corrosion.
So every good investigation needs a plan. Ours has 6 steps. First, we'll define the mission and meet our primary tool. Then, we'll gather our first major clue, the fundamental measurement. After that, we'll unmask a hidden saboteur called IR drop, learn the trick to outsmart it, and then see how to back up our findings with some corroborating evidence using coupons. And finally, we'll wrap it up by analyzing the scene of the crime, the soil itself.
Okay, first things first. What is our mission exactly? Well, we're conducting what's called a CP audit, and it all boils down to answering one single critical question. Is this structure really being protected from corrosion? To answer that, every detective needs their go-to tool. And here it is, the digital multimeter, or DMM for short. This little device is our #1 tool for gathering evidence out in the field. You can see a technician using one on the left. Its core job, as you can see in the diagram, is pretty straightforward. It takes an electrical signal, a voltage, from our structure and turns it into a clear digital number that we can read and record. It's our reliable eyes and ears on the ground.
With our DMM ready to go, it's time to collect our first and, honestly, our most important clue. This is called the structure-to-electrolyte potential. It is hands down the most common measurement you will ever take in the world of cathodic protection.
So what in the world are we actually measuring? In simple terms, it's a voltage. It's the difference in electrical potential between our metal pipe, the structure, and the dirt it's sitting in, the electrolyte. And to get a stable, meaningful reading, we use a portable reference electrode that we stick in the soil. You could think of that electrode as our trusty anchor point. It gives us a consistent baseline to measure against. This single voltage reading is our first big lead in the case.
Now, this diagram is super important because it shows you what's really happening when we take that measurement. It's a simple electrical circuit. Let's walk through it. E true, that's the real potential of the pipe, the thing we're trying to find. To measure it, we connect our voltmeter, which has its own internal resistance, that's RV. Our test leads, the wires, have some resistance, RT. The reference electrode isn't perfect. It has some resistance, RR. But the really big one to watch here is RS, the resistance of the soil between our electrode and the pipe. Why? Because all of these little resistances can, and do, introduce arrows into our reading.
And that brings us to the main villain of our investigation. I'm talking about an invisible error, a hidden saboteur that can make a pipe that's actively corroding look like it's perfectly protected. This culprit has a name, and it's called IR drop.
Just think about it for a second. You're out in the field, you take your measurement. The number on your meter looks great, and you sign off thinking the job is done. But what if that number, your most important piece of evidence, is fundamentally wrong? That's the danger of the IR drop.
This image does a fantastic job of showing the problem. See those lines radiating out from the pipe? That's the protective current flowing through the soil. As it flows, it creates these voltage gradients in the ground. It's almost like a voltage fog surrounding the pipe. Now, when we put our reference electrode down at point A, our meter doesn't just read the pipe's potential. It also picks up the voltage of the soil at that spot. In this specific example, that error adds 100 millivolts to the reading, making the pipe look way more protected than it actually is.
So let's define it properly. The IR drop error comes straight out of Ohm's law. Voltage equals current times resistance, or V equals IR. It's a voltage drop, the V, that's caused by our protective current, the I, as it flows through the resistance of the soil, the R. This error gets baked right into our measurement, and it's a huge problem because it can completely mask the true condition of our structure. Okay, so we've identified our saboteur. Now, how do we beat it? Well, we need a special kind of interrogation technique, one that forces the IR drop to show itself so we can remove it from our evidence. And that technique is called current interruption.
This graph shows you exactly how it works. Let's focus on that top waveform. On the far left, you see that high, steady line. That's the on potential. It's the number you'd normally read, and it's full of that IR drop error. Now, watch what happens at the exact moment we temporarily shut the current off. See that sharp vertical drop? That, right there, is the IR drop disappearing instantly. The point right at the top of that falling curve, just after the drop, is what we call the instant off potential. That's the prize. That's the true error-free reading we've been looking for.
The whole concept really boils down to this one simple but powerful equation. EM, our measured potential, will only equal ECOR, the true corrosion potential, if, and this is the important part, if the voltage caused by the IR drop is zero. By interrupting the current, we momentarily force that IR drop to zero, and in that split second, we can capture the true potential. This is the absolute cornerstone of doing accurate CP field.
Any good detective will tell you you never, ever rely on a single piece of evidence to close a case. You need corroborating proof. And in our world, one of the best ways to confirm our findings is by using something called a CP test coupon.
So what exactly is a CP coupon?
Well, that's pretty much what it sounds like. It's a small, carefully measured piece of metal that's the exact same type as our pipeline. We bury it in the soil right next to the pipe and wire it up. Because it's so small and we know its exact size, it acts like a perfect little stand-in for the pipeline, giving us a super accurate, localized measurement without those big, messy IR drop errors you can get on the main structure.
Now, there are two main ways we use these coupons. First, we can do that same instant off test, just like we did on the pipeline. We interrupt the current and get a really clean, IR-free reading for that one specific spot. The second method is called a polarization measurement. For this, we physically disconnect the coupon from the pipe and basically watch how fast its potential fades away. If that potential drops really slowly, that's a great sign. It means our coupon was well polarized, which is strong evidence our CP system is working great.
You can't solve a case without understanding the environment where it all went down. For us, that means we have to profile the soil. The properties of the soil have a massive influence on whether corrosion happens and how well our protection system can even work.
And the single most critical environmental factor we need to measure is soil resistivity. You can just think of it as how much the soil fights against the flow of electricity. It's a bit of a double-edged sword. Soil with low resistivity is more corrosive because it lets current flow easily, but it also makes it easier for our protective current to get to the pipe. High resistivity soil is less corrosive, but it makes our CP system work a lot harder. It's a vital piece of the puzzle.
And how do we measure it? Well, the industry standard is the Wenner 4-pin method, which you see here. It's actually brilliantly simple. You drive 4 metal pins into the ground, all equally spaced apart. You use the outer 2 pins to inject a small, known electrical current into the ground. And you use the inner 2 pins to measure the resulting voltage. That gives you a resistance value for that specific chunk of soil.
And this is how we turn that simple resistance reading into our final answer. The formula is rho equals 2 times pi times A times R. Let's break that down. Rho is the soil resistivity we're looking for. Pi is just the constant, 3.14. A is the distance between the pins, which we control, and R is the resistance number in ohms that our meter spit out. You just plug in your spacing and your resistance reading, do the math, and boom, you've calculated the soil's resistivity.
So, let's recap the investigation. Our trusted tool is the digital multimeter. Our key clue is the structure to electrolyte potential. We always have to be on the lookout for our main villain, the IR drop error. Our secret weapon to defeat it is current interruption, which gives us the true instant off potential. We back up our findings with CP coupons for localized proof, and we complete the case by analyzing the soil resistivity to understand the full picture.
So, you've done it. You've followed the steps. You've got your error-free readings, your coupon data, your soil analysis. All the evidence has been collected properly. But now comes the most important part of any detective's job: interpretation. How do you take all these numbers, all these clues, and translate them into a final verdict? Is the structure safe, or is it in danger? Well, that's a question for our next investigation.
All right, welcome to our deep dive on a really critical topic in pipeline integrity. We're going to be talking about cathodic protection for cased crossings. You know, where a pipeline goes under a road or a railroad.
We'll be using the NACE International CP2 Technician Manual as our roadmap to really understand the challenges and, more importantly, the solutions that technicians are dealing with every single day.
So where are we headed? Well, we're going to follow the exact logical path a technician would take out in the field. First, we'll get our heads around the basic problem, this paradox with the casings themselves. Then we'll shift into diagnostics, figuring out how to tell a good casing from a bad one. And finally, we'll look at the toolkit, the actual things we can do to fix a problem when we find one.
First up, let's tackle this central conflict. Case crossings are, well, a real paradox. The very piece of equipment that's designed to help protect the pipe can actually become its biggest enemy when it comes to corrosion. Let's dig into why that is.
Yeah, it really does sound completely backward, doesn't it? Why would you put a protective sleeve around a pipe that ends up shielding it from the very system that's supposed to prevent corrosion? Well, it turns out these casings are absolutely essential when you're crossing under a road or railway. They have a few jobs that are just non-negotiable.
So here are the big three reasons. First off, that heavy casing takes all the punishment from traffic pounding on the road above, so the carrier pipe inside doesn't get stressed or damaged. Second, if the pipeline ever springs a leak, the casing acts like a bucket, containing the product and preventing a catastrophic failure of the roadbed. And third, it makes it possible to replace the pipe later on without having to dig up the entire road. So you see, they're critical, but this is exactly where the headache for corrosion control begins.
And this right here is the absolute most important concept we need to grasp: electrical isolation. Think of cathodic protection, or CP, as a system that pumps protective electrical current from the soil onto the pipe. But for that current to actually get to the pipe's surface, the pipe has to be completely electrically separate from that outer casing. We do this with plastic spacers that keep the two pipes from touching, and with rubber end seals that keep dirt, water, and debris from getting inside and creating an electrical bridge. So, this really brings us to the two fundamental states a cased crossing can be in. There's the good state, the way it was designed to work, which we call isolated. And then there's the bad state, the failure mode, which we call electronically shorted. Let's take a look at what that really means.
Okay, these two images from the NACE manual show this perfectly. On the left, in Figure 4.1, you see what we want, the acceptable electrolytic couple. The pipe and casing are separate. The protective CP current, shown by those little arrows, has no choice but to travel through the soil and water, the electrolyte, to reach the pipe. That's perfect. Now look at the image on the right, Figure 4.2. This is the electronic short. The pipe is physically touching the casing. That metal-to-metal contact creates a superhighway for the current, and believe me, that is a huge, huge problem. Let's just boil this down. On the left, you've got the good setup. The current is forced to do its job, flowing through the soil and wrapping the pipe in a protective electrical blanket. On the right, the bad setup. Because the pipes are touching, the current gets lazy. It takes the path of least resistance right through that metal contact point. It completely bypasses the pipe surface, effectively creating an electrical shield that blocks any and all protection. So you might be asking, just how bad is a short really? To get a handle on that, we have to think like an electrician for a second. We have our total protective current, which we call ICP, and it has two places it can go. There's the good path through the soil, which has a certain electrical resistance, let's call it RCSG. And then there's the bad path, through the metallic short, which has its own resistance, R short, and current will always favor the easiest path.
Now, because that current can flow down both paths at the same time, we model it as a parallel electrical circuit. The formula you see here is just the standard way of figuring out how current will split itself in that situation. The main takeaway here is that since electricity is fundamentally lazy, it always takes the path of least resistance. Most of our precious protective current is going to flow through whichever path is easier. This math lets us figure out exactly how much of our current is being completely wasted.
So let's use the actual numbers from the example in the NACE manual. They say the resistance of the good path through the soil is about 1 ohm. But the resistance of that tiny metallic short, it's just 0.0001 ohms. I mean, it's practically nothing. So when you run those numbers through the formula, the result is, well, it's staggering. A full 99.999% of your protective current is lost. It just zips right through that short and does absolutely nothing to protect the pipe. It means the very structure you're trying to save is getting virtually zero protection.
Okay, so we know these shorts are incredibly bad. How in the world do we find them out in the field? Well, the first line of defense for any CP technician is to start measuring the pipe's electrical potential.
Now, this chart is one of the most powerful diagnostic tools we have. It shows what's called a potential survey.
Imagine a technician walking along the pipeline, taking a voltage reading every few feet. A healthy, protected pipe will have a nice high negative voltage. But look what happens when we get to the road crossing. Whoa! The reading takes a massive nosedive. That sharp dip is the classic, textbook signature of a shorted casing. It is a giant red flag waving at you.
Here's another key test. A technician can actually interrupt the CP system for just a second. So you measure the potential with the system running. We call that the on potential. Then you flip a switch, turn it off for a moment, and measure again. That's the off potential. In a healthy system, you should see a big jump between those two readings, at least 100 millivolts. That jump, that potential shift, is your proof that the CP current is actually getting to the pipe and doing its job. If the reading barely budges, that's a huge sign that your current is being short-circuited.
And this table from the manual really lays out the logic. Let's focus on the rows. For an isolated casing, when you turn the CP system on, you get an electronegative change. That's that big potential shift we were just talking about. It confirms the system is working. But now, look at the row for a metallic short. The potential may not change. And here's the critical part. The reading does not give CP status of pipe inside casing. This is so important. The short is effectively blindfolding you. It's hiding the fact that the pipe inside is completely unprotected.
Now, sometimes those initial on-off readings can be a little bit murky. Maybe it's not a direct metal-to-metal short, but a more resistive one. When things aren't crystal clear, we need to pull out some more advanced tests to get a final definitive answer.
So what else is in the technician's bag of tricks? Well, the NACE standard, SP2000, gives us a whole menu of options. We've already talked about the basic on-off potentials, but to really nail down a diagnosis, we can also measure how current responds to changes, or even measure the direct resistance between the pipe and casing. And for the really tough cases, there are even more advanced methods like IR drop and depolarization tests.
And this is what the setup actually looks like when you're out there. The technician puts a reference electrode on the ground, which gives them a stable electrical baseline to measure from. Then, using a voltmeter, they connect to test leads that are permanently attached to the casing and the pipe, and they take readings from both. This lets you do a direct apples-to-apples comparison of what's happening electrically to both structures.
And here's the kind of data you'd expect to get back. First, just look at the shorted column. With the CP system on, the potentials for both the casing and the pipe are exactly the same, negative 1.560 volts. They are moving in perfect lockstep, behaving just like a single piece of metal. Now look over at the isolated column. Here, the pipe's on potential is way up at negative 1.560, but the casing is only at negative 1.00. That huge difference is the smoking gun that tells you they are properly isolated and not electrically connected.
But really, the most definitive test of all just gives you a hard number. You can directly measure the electrical resistance between the casing and the pipe. And unlike potential readings, which can sometimes be open to interpretation, this is just simple math. The industry standard is right here. If you measure a resistance value below 0.010 ohms, you have a confirmed metallic short. It's a clear pass-fail. There's no gray area.
Okay, so the diagnosis is in. We've done our tests, and we've confirmed we have a short. That means we have an unprotected pipe that could be corroding as we speak. So what do we do about it? Let's talk about the fixes.
Well, in a perfect world, you can just excavate the ends of the casing, find what's causing the short. Sometimes it's just a rock wedged in there or a failed spacer, and you just clear it. Problem solved. But digging isn't always an option. If you can't fix the short, then you have to change the environment inside the casing. The next best thing is to pump the whole space full of a special corrosion-inhibiting gel or wax. This pushes out all the water and soil, and if there's no electrolyte, there's no corrosion. And if all else fails, the absolute last resort is to do a full replacement of the crossing, which is, as you can imagine, a massive and incredibly expensive job.
And all of this brings us to one final thought about the future. Modern construction methods like horizontal directional drilling, or HDD, allow us to install new pipelines under roads without using casings at all. So you might think, well, is this problem just going to go away? The answer is a hard no. There are literally hundreds of thousands of these older, cased crossings already in the ground, and they are the backbone of our energy grid. So while new builds might be different, the job of diagnosing, maintaining, and protecting this huge legacy network means these skills will remain absolutely essential for corrosion technicians for decades to come.
All right, let's talk about something that's a huge headache for every CP tech out there: stray current interference. this stuff is a silent killer for the infrastructure we're trying to protect. So in this explainer, we're going to break it all down. What it is, where it comes from, and most importantly, how to stop it. So here's our game plan. We're going to start with the absolute basics and build our way up piece by piece all the way to the advanced stuff. First things first, let's get a handle on the fundamentals. Okay, so let's tackle the big question right up front. What is stray current? And really, why should we care? What makes it so incredibly destructive to the very assets we're paid to keep safe? Okay, the easiest way to think about it is this. Stray current is electricity that's gone rogue. Imagine it escaping from its designated highway, say the rails of a transit system, and deciding to take a shortcut right through our pipeline. The key thing to remember is that our structure was never meant to be part of that circuit. It's an accidental and very unwelcome pathway. And this is super important. You can't mix this up with regular galvanic corrosion. Think of galvanic corrosion as an internal problem. It's like tiny little batteries forming all over your pipe's surface. Stray current, on the other hand, is an external attack. It's an invasion from an outside source. And we're not talking about tiny currents here. We can be talking about amps, not milliamps. The source, the power, the scale, it's a whole different ballgame. And if you want to know just how bad it can get, well, Faraday's law lays it out in pretty stark terms. Just look at this. A single amp, just one, of DC stray current jumping off a steel pipe can eat away 20 pounds of steel in a single year. That's not a pinhole leak we're talking about. That is aggressive, rapid metal loss that can lead to a catastrophic failure way faster than you'd expect. So how do we fight this? Well, you can't just go in swinging. It's not about guesswork. It's about being a detective. A good stray current analysis is a methodical investigation, and it follows a very specific roadmap to get to the bottom of the problem. You really have to go through the checklist. First, where's this current coming from? Second, where is it jumping onto our structure? That's the pickup point. Third, where is it jumping off? That's the discharge point, the danger zone. Fourth, how much current are we talking about? And only when you have all those answers can you even begin to think about a solution. All right, let's dive into the first category you're likely to run into. Dynamic stray currents are a real pain because, as the name suggests, they're always moving, always changing. The sources are things that cycle on and off, like welding, mining gear, or the textbook example you'll see everywhere, DC-powered transit systems, like subways. This picture right here is the classic scenario. You've got a train pulling power from an overhead line. Now, that electricity is supposed to travel back to the substation through the rails. But nothing's perfect. The rails aren't perfectly insulated from the ground, so some of that current says, hey, I'm going to find an easier way home. And what's buried right there? Our nice big conductive pipeline. It becomes the path of least resistance. And this graph, this is its signature. This is what you'll see on your multimeter out in the field. A healthy, protected pipeline should give you a nice, steady pipe-to-soil potential. When you see your readings bouncing all over the place like a seismograph during an earthquake, that's a huge red flag. It's practically screaming at you that there's an external, intermittent power source messing with your system. Now, moving on from those jumpy dynamic currents, we have static interference. This is a much more stable, constant problem. The source isn't turning on and off. 9 times out of 10, this is a case of good fences make good neighbors, because it's usually another company's cathodic protection system bleeding over and affecting yours. Okay, pay close attention here, because this slide shows the two sides of the coin. On the left, you've got current discharge. The neighbor's anode bed is pumping out current, and it forces that current to literally jump off of our pipe to get to their pipeline. That exit point, that's where our pipe is turning to rust. Now look at the right. This is current pickup. Their protected pipeline is so negative that it's actually pulling current onto our pipe. Now at this pickup spot, we're okay. But here's the kicker. For every electron that gets on, one has to get off somewhere else. And our job is to find that somewhere else, because that's our new corrosion hotspot. So we know what we're looking for. How do we actually find it in the real world? Well, the number one tool in our toolbox is what we call an on-off test. It's simple in theory. We measure our pipeline's potentials with the other company's CP system running, and then we measure it again when they turn it off. Of course, this means you got to coordinate with the other guys, which can sometimes be the hardest part. This table is a perfect example of the kind of data you'd collect. We've got 3 locations. The off column is our baseline. That's our pipe's normal potential. The on column is what happens when the neighboring rectifier gets switched on. So what is this data telling us? It all comes down to the shift. Look at location X. Our potential went from negative 1100 to negative 1600. It got more negative. That's the classic sign of current pickup. no corrosion happening there. But now, look at location Y. It went from -1,000 all the way to -400. It shifted in the positive direction. It became less negative. That, my friends, is the flashing red light. That's our discharge point. That's where our pipe is actively corroding. And location Z? No change at all. It's just too far away to be affected. So now we know where it's happening, but we need to know how much current we're losing. For that, we use a fundamental electrical law, Kirchhoff's law. It sounds complicated, but the idea is simple. Current doesn't just disappear. If you measure the current flowing along the pipe at point A, and then you measure it again down the line at point B, and the number is lower, that missing current had to go somewhere. And in our world, that somewhere is into the soil. By taking these measurements, we can calculate exactly how many amps are leaving our pipe in that section. Okay, detective work is done. We've found the source, we've mapped the crime scene, and we know the severity of the problem. Now what? Time to fix it. The goal is to provide that lost, stray current a safe, easy way to get back home, a way that isn't through our pipe wall. And the most common solution is an electrical bond. But you absolutely have to get this right, and this slide shows why. It's all about polarity. In case 1, the bond is installed correctly. It provides a nice metallic path for the current to drain safely from our pipe back to its source. Perfect. But look at case 2. If you wire it up backwards, you don't just fail to solve the problem, you make it 100 times worse. You've essentially created a superhighway for corrosion. The rule is simple, and you can't ever forget it. The bond must always allow current to flow from the more negative structure to the less negative one. And here's what that bond looks like in the real world. It's basically just a cable that connects the two structures, usually run through a test station where we can install a resistor. That resistor is key because it lets us dial in the exact amount of current we want to drain off. It's a simple, elegant solution. We've given the current a better road to travel on, and it'll take it every time. Now, everything we've talked about so far has been DC current, but there's another threat out there, AC interference. This is a whole different animal. It usually comes from running a pipeline in the same corridor as high-voltage AC power lines, and it brings a double threat, a serious safety hazard for personnel, and a unique type of corrosion. What's happening here is a process called electromagnetic induction. The easiest way to picture it is to think of the whole setup as a giant, unplanned transformer. The power line is the primary coil. Our pipeline becomes the secondary coil. The massive magnetic field pulsing from the power line literally induces a voltage right onto our pipe. You can't see it, but it's there, and it can be extremely dangerous. So to fight AC, we need a different set of tools. We use devices called decouplers or polarization cells. Think of them as smart switches. They're designed to block our low-voltage DC for cathodic protection. We don't want that draining away. But if they sense any high-voltage AC, they instantly close and short-circuit that dangerous current safely to a grounding system. And for personnel safety, we install grounding mats at any above-ground appurtenance, which keeps technicians safe from dangerous touch potentials. So let's wrap this up. What are the big takeaways? Stray current is an external threat, totally different from galvanic corrosion. The real damage happens where DC current discharges from your structure. Finding it involves systematic field analysis, looking for those potential shifts. And the fix, for DC, is usually a properly installed bond. AC is a unique safety and corrosion hazard that needs its own special mitigation tools. And, looking to the future, this is a problem that's only going to get bigger. Think about it. High-speed rail, massive solar and wind farms with HVDC transmission lines, more and more electric vehicles. The world is becoming more electrified every day. For CP professionals, staying on top of this stuff isn't just a good idea. It's absolutely critical if we're going to protect our vital infrastructure. All right, welcome. Today we're going to open up the Pipeline Inspector's Toolkit. It's really a masterclass in the key techniques that are used to check on the health of this huge invisible network of pipelines buried right under our feet. So let's dive right in. So here's the roadmap for our session. First, we're going to talk about the big challenge. How do you even inspect something you can't see? Then we'll get into the details of the main survey methods: SIPS, DCVG, ACVG, and ACCA. And to wrap it all up, we'll look at how the pros take all this different data and put it together to get the real big picture of a pipeline's health. Okay, so first things first, let's really set the stage here. The whole reason these techniques even exist is to solve one fundamental problem. We're trying to assess a piece of critical infrastructure that is totally, completely buried and invisible. So that's the big question, right? How in the world do you inspect something you can't even see? Well, the answer is pretty cool, actually. It's all about listening to its electrical signals. What you're seeing here is a technique called a closed interval potential survey, or CIPS for short, and it's one of the main ways we can essentially see what's going on with the pipeline right through the ground. So these are the big players in our toolkit for external surveys. You can kind of think of them like different tools a doctor would use. CIPS, that's your overall health checkup. DCVG and ACVG, those are like the precision scalpels for finding very specific injuries. And ACCA, well, that's for checking the pipeline's electrical circulatory system. We're going to get into each one of these. All right, let's kick things off with the real workhorse of pipeline surveys, CIPS. Now, its whole job is to give us a super detailed, continuous profile of the pipeline's cathodic protection system. And just as a quick refresher, that's the system that actively prevents the pipe from corroding. It's absolutely critical. You know, the name really gives it away, closed interval. We're not talking about taking a measurement here and then another one a mile down the road. No, with a CIPS survey, you're getting a reading every meter, every few feet. Think about it like this. It's the difference between taking someone's blood pressure on just their arm versus taking it all the way up and down their entire body. You get this incredibly detailed profile, which means you're not going to miss those small, localized problems. Okay, but here's where it gets a little tricky. There's a big challenge we have to deal with. The very same electrical current that's protecting the pipe can actually mess with our measurements. This interference has a name. It's called the IR error. The best analogy is trying to hear a whisper in a really loud room. If we don't figure out a way to filter out that background noise, we could get a completely wrong idea. We might think the pipeline is perfectly protected when in reality, it's quietly corroding away. So how do we do it? How do we filter out that noise? Well, it all comes down to some pretty basic physics, actually. We use a fundamental electrical formula. It's basically a version of Ohm's law to calculate the exact amount of current that's causing the problem. Once we know the precise level of that noise, we can just subtract it from our reading. Simple as that. Let's break this equation down into simple terms. To find that pesky interfering current, which we call IAP, you really only need two pieces of information. First, the voltage drop, or V, which you measure over a specific section of the pipe, and second, the electrical resistance, R, of that exact same section of pipe. You take the voltage, you divide it by the resistance, and boom, you've just calculated the exact current that's causing your IR error. So picture this, a technician is out in the field. They measure the voltage drop along the pipe. They already know how to calculate the pipe's resistance, because that's based on its size and what it's made of. Then they just do the math, divide one by the other, and what they get is a very precise number for that interfering current. That's the noise they can now confidently remove from their data to see the true picture. And this plot right here, this is what it all looks like in practice. See that red line? That's the on potential. That's our measurement with all the electrical noise included. Now look at the green line. That's the off potential. That's our clean, true reading after we've subtracted the noise. So that gap between the red and green lines, that is the IR error we calculated. And the whole point of this is to watch that green line. If it dips below the safety threshold, which is usually negative 0.850 volts, that's when you know you've got a problem. But CIPS plots aren't just about finding small issues. They can be incredibly powerful diagnostic charts. I mean, just look at this. See that sudden, massive drop in the potential? That's not a tiny little corrosion spot. No way. That is a giant red flag that something major has gone wrong. We're talking a systemic failure, like a DC power source just completely died, or there's a huge electrical short somewhere. Okay, so CIPSS is great. It tells us if there's a problem, and it gives us a pretty good idea of where it is. But what if that problem is a really tiny hole in the pipeline's protective coating? For something that specific, you need a more focused, more precise tool. And that's where DCVG and ACVG come into play. And this really is the key difference to understand. If CIPS is your wide-angle lens giving you the big picture and asking, hey, is the overall protection system working? Then DCVG is your zoom lens. It gets right in there. DCVG stands for direct current voltage gradient, and its job is to ask a much more specific question. Exactly where is the current leaking out of a hole in the coating? So here's the clever part. A surveyor walks along the pipeline with two probes stuck in the ground. They're measuring the voltage gradient in the soil. Now, when current escapes from a tiny defect in the coating, inspectors have a great name for this. They call it a coating holiday. That leaking current creates an electrical field in the soil. The surveyor's equipment picks this up, and all they have to do is follow that signal to where it's strongest. It literally leads them right to the epicenter of the leak. They can pinpoint the defect with incredible accuracy. There's a similar tool that does pretty much the same thing, and it's called ACVG for Alternating Current Voltage Gradient. As you can guess, instead of DC, this one uses an AC signal. The technician uses this cool-looking piece of gear called an A-frame. As they walk along, the A-frame is listening for the electromagnetic field from that AC signal. And when they walk right over a coating defect, the receiver detects a huge spike in the signal. It's basically like the machine yelling, "Hey, the problem is right under your feet." Okay, so let's recap. We've used SIPs to check the overall health of the protection system. We've used DCVG to zoom in and find the exact location of any holes. So now let's talk about another method that gives us a sense of the coating's quality over a whole section. And for that, we turn to ACCA. Probably the easiest way to get your head around ACCA, which stands for Alternating Current Attenuation, is to use an analogy. Just imagine that the protective current we're putting on the pipe is like a sound traveling through it. If the coating is in great shape, it's like a perfectly insulated tube. It keeps all the sound in. But if there are faults or defects, the sound starts to leak out. ACCA is basically the microphone we use to listen for where that sound is escaping the most. And this visual shows you exactly what I'm talking about. We apply an AC signal at one end of the pipe. Now, naturally, as you get further and further away from the source, that signal is going to get weaker. It attenuates. That's normal. But then, look at the plot. See where there's a coating defect? All of a sudden, a bunch of current leaks out into the soil. And what that does is it causes a really sharp drop in the signal strength on the pipe. That sudden drop is the smoking gun that tells the surveyor, hey, this whole area has a really poor coating. You see, each one of these tools we've talked about gives us a really important piece of the puzzle. But the real skill, the true masterclass, comes from knowing how to put all of those pieces together. This is where we move from just collecting data to actually understanding the big picture, a truly complete view of the pipeline's health. The official name for this is External Corrosion Direct Assessment, or ECDA. And this chart is a perfect example of how it works. What you're seeing is multiple layers of data, all for the exact same stretch of pipe. An expert analyst will look at this and see, okay, the SIPS data shows a low potential right here. Then they see the ACCA data shows a big current loss in the same spot, and then the DCVG data pinpoints a defect at that exact location. When you have all three tools screaming about the same spot, that's when you can say with almost 100% confidence, okay guys, dig here. Now, everything we've talked about so far has been about inspecting the pipe from the outside, from above ground. But what if you could actually go inside the pipe? Well, you can. That's the job of inline inspection, or ILI. We send an intelligent robotic tool, which everyone in the industry calls a pig, to travel right through the pipeline. One of the most common technologies it uses is called magnetic flux leakage, or MFL. The pig creates this super powerful magnetic field inside the pipe wall. If there's any metal missing, whether from corrosion on the inside or the outside, it causes that magnetic field to leak out. The pig has sensors that detect that leak, and it can tell us not just where the damage is, but also how big it is. So let's do a quick final review of our inspector's toolkit. CIPs, that gives us the big picture health profile, but remember, it can be thrown off by electrical noise. DCVG and ACVG, fantastic for pinpointing the exact location of a defect, but they don't really tell you how big or severe it is. ACCA, great for finding whole sections with a weak coating, but its signal can get weaker if the pipe is buried really deep. And finally, IOI. This gives us the ultimate inside-out inspection, but the big limitation is that you can only use it if the pipeline was actually designed to be piggable in the first place. So we've covered this really powerful set of tools that are all about finding and fixing corrosion that's happening right now. But that leaves us with one last really important question to think about. As all this technology gets better and as our ability to analyze all this data improves, can we finally move beyond just reacting to problems? Can we get to a point where we can accurately predict where the next weak spot is going to be? Because that is the real key to making sure these vast, unseen networks are safe for many, many years to come. All right, welcome. Today, we're diving deep into Cathodic Protection. This is the incredible, unseen technology that's constantly working to prevent catastrophic failures in everything from our critical pipelines to massive offshore platforms. We're going to break down exactly how these systems work, starting with the fundamental science and building all the way up to some complex real-world engineering. So, here's our game plan. We'll kick things off with the foundational concepts. You've got to know the basics. Then we'll explore the two main ways to do this: galvanic systems and impressed current systems. After that, we'll look at how these are actually installed out in the field, and we'll wrap it all up by summarizing the key takeaways and some really important environmental factors you have to consider. Okay, Section 1, the absolute basics of corrosion control. Look, before we can figure out how to stop rust, we need to understand what corrosion is on an electrochemical level. You have to get this right, because everything else we talk about today builds on this one core idea. So, what's the deal with cathodic protection, or CP as we call it? At its heart, it's an electrochemical trick. Think of any piece of rusting metal as a tiny natural battery, what we call an electrochemical cell. This little battery has 4 parts: an anode, which is where the metal literally dissolves and releases electrons, a cathode, where a different chemical reaction happens, a metal path for those electrons to travel, and an electrolyte, like soil or water that lets ions move around. Now here's the key. Corrosion, the bad stuff, only happens at the anode. So cathodic protection works by forcing our entire structure, whether it's a pipeline or a storage tank, to become the cathode of this cell. By pumping it full of electrons from somewhere else, we stop it from ever becoming an anode. We're basically overpowering the natural urge to rust. Okay, so now that we've got the theory down, let's look at the first way we actually do this in the real world. This is the galvanic system. It's kind of elegant in its simplicity because it uses the natural properties of metals to provide protection without any outside power at all. Now, take a look at this diagram. It's super important because it shows the whole circuit in action. You've really got 2 circuits here. The first is the metallic circuit. You see the structure we want to protect, and then connected to it by a wire is our galvanic anode. This anode is made of a metal that is, by its very nature, more willing to corrode than our structure is. The wire lets electrons flow from that anode over to our structure. The second part is the electrolytic circuit. Both the anode and the structure are buried in an electrolyte, say wet soil. In this part of the circuit, the anode sacrifices itself. It dissolves into positive ions that then travel through the soil to the structure, and that movement completes the electrical circuit. It's this continuous flow of electrons onto our structure that keeps it safe. This quote right here, this is the entire secret sauce of a galvanic system. We are deliberately using a basic electrochemical principle. You see, when you connect 2 different metals in an electrolyte, the one that's more active, or less noble, you'll sometimes hear, that one automatically becomes the anode and starts to corrode. The other one becomes the cathode and gets protected. We are literally building a corrosion cell on purpose just to make sure our valuable asset is the part that gets protected. Now, this table, this is where the engineering really starts. It's how we pick the right tool for the job. Let's walk through it. The column on the right shows the natural electrical potential of different metals in volts. Think of this as how badly each metal wants to give away its electrons. Now look at the bottom row, our reference, rusted carbon steel. That's our patient. It sits at about -0.2 to -0.5 volts. Now look at the metals above it, magnesium, zinc, and aluminum. See how their numbers are much more negative? That means they are way more electrochemically active. This difference in voltage is what we call the driving voltage. So if you connect magnesium at, say, -1.75 volts to steel at -0.5 volts, you get a difference of 1.25 volts. That voltage is the push that drives the protective current from the anode to the steel. The bigger that difference, the more current you can get. So what's the big takeaway here? Well, that relatively low driving voltage of galvanic systems really defines where we can use them. They're most effective in a couple of situations. First, for smaller or really well-isolated structures that don't need a ton of current. And second, in places where the electrolyte has very low resistivity, like in seawater or really marshy soil. Now, resistivity is just a measure of how hard it is to push electricity through something. Think of it like trying to push water through a tiny straw versus a fire hose. High resistivity soil is like that tiny straw. Because galvanic systems have a low voltage push, they just can't get enough current through that high resistance soil to protect a large structure. All right, so galvanic systems are great, but what if you have a massive pipeline stretching for miles, or you're in really dry, resistive desert soil? Well, that's when we bring out the big guns, Impressed Current Cathodic Protection, or ICCP. This is the heavy-duty solution. The first thing you'll notice in his diagram is the big new box in the middle, an external DC power source. This is almost always a device called a rectifier. A rectifier's job is simple. It takes the alternating current, or AC, from the power grid and converts it into the direct current, or DC, that we need for cathodic protection. The positive side of the rectifier gets hooked up to our anode, and the negative side gets hooked up to the structure we're protecting. This lets us impress a much higher voltage and current into the ground than we ever could with a simple galvanic anode. And that gives us 2 huge advantages. We can protect enormous structures, and we can fine-tune the amount of protection just by turning a knob on the rectifier. Now, this change in power source, it completely flips the script on what kind of anodes we use. Galvanic anodes are, by their very definition, designed to be consumed. They're supposed to disappear over time. But impressed current anodes, they are designed not to be consumed, or at least to be consumed at an incredibly slow rate. That's why we often call them dimensionally stable. They can pump out a huge amount of current for years, even decades, without really changing their shape or size. So what are these super durable anodes made of? Let's run through the big ones. Mixed metal oxide, or MMO, is a very common choice. It's basically a special coating on a titanium rod, extremely durable and works almost anywhere. High silicon cast iron is another workhorse, a tough and cost-effective option we use a lot underground. Platinum, usually plated onto a titanium core, is super efficient but also pretty pricey, so you see it in critical spots like protecting ship hulls. And finally, there's graphite, a lower-cost option that you'll often find in certain soil applications. Okay, now just like with the other system, we don't just stick these anodes in the ground naked. They get a special bed to lie in called a backfill, and this table tells you why it's so important. This backfill, which is usually made of a carbon material called coke, does two critical jobs. First, it lowers the overall electrical resistance by basically making the anode seem much bigger to the surrounding soil. This makes the whole system more efficient. Second, the carbon in the backfill actually gets consumed before the anode material itself, which stretches out the life of our expensive anode even longer. And remember this, the more you compact this backfill, the lower the resistance will be. So we know the types of systems, we know the parts. Now, how do we actually lay them out in the field? Because where you put the anodes, what we call the configuration, well, it changes everything. It's an absolutely critical part of the design. We've got two main strategies, and you can see them side by side right here. On the left, you've got what's called a distributed anode system. Think of it like having lots of little helpers spread out all along the pipeline. On the right, you have a remote system. This is where you group all your anodes together in one spot, called a ground bed, and place it a good distance away from what you're protecting. It's like having one giant spotlight protecting a huge area. Choosing between these is a major engineering decision. So let's focus on the distributed system first. The key word here is close. The anodes are installed right up next to the structure. Now, why would you do that? Well, it's all about precision and control. By keeping the anodes close, you make sure that protective current goes exactly where you want it and doesn't wander off and cause problems for other pipes or structures nearby. This makes it the perfect choice for things like old, uncoated pipelines or in really congested urban areas. And now for the remote system. This is the complete opposite approach. You put your anodes way, way out there. It sounds weird, but think of it like a light bulb in a big dark room. The farther away that bulb is, the more evenly it lights up the whole space. It's the same idea with current. A remote ground bed throws a wide, even field of protection over a massive area. This is by far the most efficient way to protect long, well-coated structures like cross-country pipelines, where you can protect miles and miles from just one spot. All right, we are in the home stretch. Let's pull all of these ideas together. We're going to do a quick recap of the systems, and then we're going to talk about something really important. The actual chemistry that's happening right at the anode surface and why we have to be really careful about it. Okay, so for this whole system to work, electrons have to come from somewhere. And they come from a chemical reaction happening at the anode. There are really two main ways this can go down. The first is metal oxidation. The equation, M becomes M plus an electron, just means the metal of the anode, M, is literally dissolving into a positive ion, M plus, to release that protective electron. This is what happens with our sacrificial galvanic anodes. The second reaction, which is the main one for our stable impressed current anodes, is water hydrolysis. Here, two water molecules get ripped apart at the anode surface, and what you get is one molecule of oxygen gas, 4 free electrons, and 4 positive hydrogen ions, H+. And what are hydrogen ions? Well, my friends, that is acid. So this chemistry isn't just a textbook exercise. It creates real-world byproducts that we have to manage. For instance, if you're in salt water, which has chloride in it, that reaction can produce hazardous chlorine gas. If you're using a carbon backfill, it can be consumed and produce carbon dioxide. These gases have to go somewhere, which is why deep anode ground beds are always built with a vent pipe to let them escape safely. And that acid buildup we just talked about, it can eat away at anode cables and really mess with the system's performance if it's not designed correctly. And here it is, the final showdown. This is your go-to cheat sheet for comparing these two systems head-to-head. You've got the power source, the driving voltage, the anode type, and the typical use. Just remember the core difference. Galvanic is natural, low power, and uses anodes that get consumed, making it perfect for smaller jobs. Impressed current is externally powered, high power, and uses long-life anodes, making it the choice for the really big jobs. Understanding this table is everything when it comes to choosing the right system. To wrap all this up, I'm going to leave you with a little real-world puzzle. Think about this scenario. You have a brand new pipeline, and it's got a fantastic coating, but it's running through a crowded city. So, the great coating might make you think a remote ground bed would be super efficient. But the congested urban area brings a huge risk of causing problems for other utilities, which would make you think, I've got to use a distributed system. So what do? Which system and layout provides the best protection without causing collateral damage? That tension, right there, is the heart of what cathodic protection engineers figure out every single day. All right, let's talk about the absolute heart of any impressed current cathodic protection system, the DC power source. This is the one piece of the puzzle that decides whether a massive pipeline lasts for decades or just, well, corrodes away. We're going to cover the whole shebang, from the big, heavy-duty rectifiers you see everywhere, all the way to some really clever off-grid solutions for protecting stuff way out in the middle of nowhere. So here's our game plan. We'll kick things off with the basics, like why DC power is the only game in town for this kind of work. Then we'll get into the modern high-tech switch mode supplies and see how they stack up against the classic transformer rectifier. After that, we're going off-grid to check out remote power options. Then it's time to put on our technician's hat and do some real-world troubleshooting. And we'll wrap it all up with a super important skill, how to measure efficiency, so you know your system isn't just running, but running right. Okay, let's dive right in. The whole idea behind impressed current cathodic protection, or ICCP, is to force the structure you're protecting, say a pipeline, to be the cathode in an electrical circuit. We do that by pumping a direct current from an anode through the soil or water and onto that pipeline. Now that word direct is everything. It has to be a one-way street. Think about it. If you used AC, which flips back and forth 60 times a second, you'd be protecting your pipe for half the time and corroding it the other half. That would be a disaster. So yeah, without a stable one-way DC source, the whole thing just doesn't work, period. Now let's check out the new kid on the block, the Switch Mode Power Supply, or SMPS. If you're used to those big, heavy transformer rectifier boxes, these things are a whole different animal. They use some pretty cool high-frequency electronics to do the same job, but as you'll see, they come with their own set of pros and cons. So what is the big deal here? This slide cuts right to the chase. Your traditional rectifier, it's built around a massive iron core transformer that chugs along at the grid's low frequency, 50 or 60 hertz. But in SMPS, it operates at insanely high frequencies. We're talking 50 to 500 kilohertz. And here's the cool physics part. The higher the frequency, the smaller your magnetic parts, like transformers, can be to handle the same amount of power. That's the secret sauce. That's why they're so much smaller and lighter. Let's follow the electricity through this thing. First, the AC from the wall gets turned into a rough, high-voltage DC. Now, the star of the show is the switching transistor, labeled TR. Think of it as a light switch that's being flicked on and off thousands of times a second. It chops up that DC into high-frequency pulses. Those pulses then get smoothed out by the inductor and capacitor. The inductor smooths out the current, and the capacitor smooths out the voltage. The end result is a really clean, stable DC output. And the whole time, a little control circuit, the brain of the operation, is watching the output and tweaking the switch's timing to keep that voltage perfect. So how does it control the voltage? It all comes down to something called the duty cycle, which we're calling D here. It's actually pretty simple. The output voltage, V out, is just the input voltage, V in, multiplied by that duty cycle. And the duty cycle is just the fraction of time the switch is on versus the total time. So if the switch is on for just a tiny bit of each cycle, you get a low voltage out. If it's on for longer, you get a higher voltage. By adjusting this on time, thousands of times per second, the SMPS can hold that output voltage rock steady, no matter what's happening down the line. And this brings us to the trade-offs, because there's always a trade-off, right? The good stuff is obvious. They're small, light, and really efficient. But that high-frequency switching is a double-edged sword. It can create a lot of electrical noise, or EMI, which can mess with nearby radios or sensitive equipment. And because they're so complex, they've got more parts that can fail. If one breaks down in the field, you're not fixing it with a spare part from your truck. You're usually just replacing the whole unit. Okay, let's switch gears and talk about the industry standard, the old faithful, the transformer rectifier, or TR unit. These are the rugged, reliable workhorses you'll find on most job sites. They're not as fancy as an SMPS, but they get the job done. Let's pop the hood and see what's inside. You know, every TR unit really only does 3 basic things, one after the other. First, it's got to protect itself from things like power surges. Second, it uses that big transformer to step the voltage down to a useful level. And third, it uses some rectifying parts, usually diodes, to finally change that AC power into the DC power we need. Simple as that. Job number 1, protection. And that starts with the circuit breaker. You've got 2 main types here. On the left is a thermal breaker. If there's a slow, steady overload, a little metal strip inside heats up, bends, and eventually trips the switch. On the right, you have a magnetic breaker. This one reacts to a huge, sudden spike in current, like from a lightning strike. That current creates a powerful magnetic field that trips the breaker instantly. That's why magnetic ones are usually what you want protecting the guts of a rectifier. Next up is the big guy, the heart of the unit, the transformer. Its main job is to take that high voltage from the power line and step it down to a much lower, safer AC voltage. It does this with 2 coils of wire, a primary and a secondary, wrapped around an iron core. It also provides electrical isolation, which is a really important safety feature that keeps the high voltage grid separate from our cathodic protection circuit. The real magic of a transformer is all about its turns ratio. The voltage changes based on how many loops of wire are on the secondary coil compared to the primary one. Let's walk through this example. We've got 115 volts coming in on the primary side, which has 400 turns of wire. The secondary side, which goes to our circuit, only has 100 turns. That's a 4-to-1 ratio, right? So the voltage also gets stepped down by a factor of 4, giving us 28.75 volts. It's a beautifully simple and super reliable principle. And now we get to the most important step, turning that AC into DC. We do this with a rectifier, and the most common kind you'll see is this one, a full-wave bridge. It's just 4 diodes arranged in a special way. Now, a diode is basically a one-way street for electricity. This clever setup uses those 4 one-way streets to take the AC current, which is flowing back and forth, and force it to flow in only one direction. This picture shows you exactly what that bridge rectifier is doing. See the smooth, wavy line at the top? That's your incoming AC. Now, during the positive part of the wave, current flows through 2 of the diodes. But during the negative part, the other 2 diodes kick in and steer the current so it still flows in the same direction. What happens is, the whole negative half of the wave gets flipped upside down. The result is the bumpy wave at the bottom. It's not perfectly smooth, but look, it never goes negative. It is now direct. So far, we've kind of assumed you can just find an outlet and plug your rectifier in. But what happens when your pipeline is out in the desert, miles from anything? For that, we've got to go off-grid. The 2 main ways to do this are with solar power or with something called a thermoelectric generator, or a TEG. The solar setup on the left is pretty familiar. Panels soak up sunlight, charge batteries, and the batteries provide power 24/7. The TEG on the right, though, is really cool. It burns fuel like natural gas to create heat. That heat creates a temperature difference across a special material, and through a process called the Seebeck effect, it generates DC electricity directly. There are no moving parts. They're incredibly reliable, which makes them perfect for really remote, harsh places where you can't count on sunshine. Okay, enough theory. It's time to get our hands dirty. Rectifiers are tough, but things still break. Knowing how to figure out what's wrong and doing it in a logical way is a skill every CP tech needs. All right, picture this. You get to a job site, and you're looking at a classic problem. The rectifier's on, the lights are on, but the meters say 0 volts and 0 amps. Nothing's going out. It could be a bunch of different things, and just poking around randomly isn't going to help. You need a plan. A lot of the time, the culprit for a 0 output problem is a failed diode in that rectifier bridge. They can fail open, like a blown fuse, or they can fail shorted, where they just let current flow both ways. So one of your very first checks is to test those diodes. And I can't stress this enough, after you make absolutely sure the power is off and locked out, you can test them with a multimeter just like you see here. So what are you looking for on your meter? Here's the cheat sheet. When you're on the diode check setting, a good diode will show a small voltage drop when you test it the right way, usually about half a volt. When you swap the leads, it should read OL for over limit, meaning it's blocking the current like it's supposed to. If you see almost 0 volts both ways, that diode is shorted. If you see OL both ways, it's open. Either way, if it's not good, it's got to be replaced. Last but not least, let's talk performance. Look, a rectifier might be putting out the right numbers, but that doesn't mean it's healthy. Measuring its efficiency is like taking its pulse. It tells you how much of the power you're paying for is actually being turned into protection. The formula couldn't be simpler. It's just the power coming out divided by the power going in. The DC power out is the good stuff, the useful work being done. You figure that out by multiplying the DC volts by the DC amps right off the meters. The AC power in is what the power company is charging you for. The difference between those two numbers is wasted power, mostly lost as heat. Let's make it real. Say your rectifier's meters read 25 volts and 10 amps. Multiply those and you get 250 watts of useful DC power. Great. But then you measure the AC power going in and you see it's actually pulling 500 watts. You do the math. 250 divided by 500. That's 0.5, or 50% efficiency. That means for every dollar you spend on electricity, 50 cents is literally just being used to heat up the rectifier box. A healthy unit should be up in the 70–80% range. A big drop like that is a huge red flag that something's wrong inside. And really, that's what this all boils down to. It's not enough to just see that the system is turned on. A real pro understands how it works, knows how to fix it when it breaks, and knows how to check its performance to make sure it's not just running, but that it's running right, protecting our critical infrastructure efficiently and effectively. All right, let's dive right in. Today, we're tackling a huge topic, the monitoring and record-keeping for cathodic protection systems. Now, this isn't just about ticking boxes or filling out forms. This is about having hard proof that your corrosion defense system is actually doing its job. And that quote, it pretty much says it all. Without consistent, detailed monitoring, you're basically just crossing your fingers and hoping that multi-million-dollar asset is safe. Monitoring is what turns that hope into cold, hard, data-driven proof. So here's our game plan. We're going to start with the basics. What are we even trying to achieve? Then we'll get into the prep work for a field survey and the actual techniques you'll use out there. After that, it's all about the crucial art of keeping good records, and we'll wrap it all up by talking about the rules and regulations you have to follow. Okay, first things first. Before we can even talk about how to monitor a system, we've got to be crystal clear on what a successful system even looks like. What's the goal we're shooting for? A healthy CP system really boils down to these 6 key things. It's not just about cranking up the current. You have to provide enough current, and you've got to make sure it's spread out efficiently. You also have to be careful it's not causing problems for other nearby structures. And of course, the system needs to be built to last, be flexible enough for future changes, and this is the big one, it has to be on all the time. Continuous operation is absolutely non-negotiable. So how do we check up on these goals in the real world? Well, it all starts with homework. Seriously, the most successful fieldwork actually begins at a desk, long before you ever step foot outside. It's all about gathering intelligence first. Step 1 is simple. You have to know the structure you're protecting inside and out. That means digging into the original designs, understanding exactly how it's put together, and looking at its entire history. Every one of these points tells a part of the story. The material and the coating tell you about its natural defenses, but the leak history? Oh, that's gold. Think of it as a treasure map that points you directly to potential corrosion hotspots. And of course, you've got to know where your test points and isolators are just to plan an efficient day. Okay, so you know the structure, but that's only half the battle, right? Because that structure doesn't exist in a bubble. The next step is to understand the world it lives in, an environment that is constantly trying to attack your asset. This is all about identifying external threats. Are there other pipelines nearby that could cause interference? High voltage power lines that could mess with your readings? What about a nearby rail system that throws off stray DC currents? Pinpointing these things before the survey is what separates clean, reliable data from a complete waste of it. All right, prep work is done. Time to get our boots dirty. This is where we go out and collect the actual data that's going to tell us whether or not the system is working as designed. This right here is the moment of truth. Every single measurement you take with that multimeter and reference electrode is a critical piece of the puzzle. The integrity of your entire corrosion prevention program hinges on getting accurate, reliable measurements right here in the field. Now, this is absolutely crucial to understand. You don't monitor every system the same way. Let's take a common problem, like a short circuit, where your pipe accidentally touches some other metal. With a sacrificial anode system, you'll see the potential become less negative. But with an impressed current system, the potential actually shifts in the positive direction. Knowing these different symptoms is what lets you troubleshoot problems quickly and accurately. So you've spent the day collecting all this great data. Now what? Well, this next part is arguably the most important step in the entire process. Because, let's be real, if the data isn't recorded properly, the survey might as well have never happened. Your records really have three main jobs. First, they're technical, for the folks who manage the system day to day. Second, they're historical, building a timeline that lets you spot trends and figure out what went wrong when there's a problem. And finally, and this is huge, they are legal. They are your proof of compliance for regulators. Technical, historical, legal. Remember those three pillars. So what's the difference between a good record and a useless piece of paper? It's all about the details. Think of this as your personal checklist. Did you get the polarity right? Are the units clearly marked? What kind of reference cell did you use? And where exactly did you take that reading? Answering these questions every single time is what makes your data solid, defensible, and valuable for years to come. And all of this brings us to our final section, the rules of the road. Because in most industries, all this monitoring and record keeping isn't just a good idea, it's the law. This table tells a really important story. You can never, ever assume the rules are the same everywhere. For a regulated pipeline in the US, you're checking that rectifier 6 times a year. But hop over the border to Canada, and suddenly it's a monthly check. This just hammers home the point that you have to know the specific regulations for your specific location and industry. Now, you're going to hear this acronym thrown around a lot in regulatory documents. ECDA. It stands for External Corrosion Direct Assessment. The best way to think of it is as a formal 4-step checkup for a pipeline. It uses a lot of the data we've been talking about to figure out the health of the pipe without having to dig the whole thing up. It's a really key process. So, what's the bottom line on how long you keep all this paper? For the most critical documents, we're talking leak reports, CP system designs, major inspection results, the rule is simple. You keep them for the entire life of the asset. Not 5 years, not 10 years. For life. This data becomes a permanent part of that asset's history. And that leads to a final thought to chew on. We've talked a lot about the nitty-gritty of collecting and recording data, but with remote monitors and big data becoming the norm, the job itself is changing. So the question for the future is, how does the role of the technician shift? Does it move away from just collecting data points and more toward analyzing trends and becoming a true data expert? It's definitely something to think about. Welcome. Today, we're going to break down the single most critical topic for any cathodic protection technician, and that is field safety. Look, this isn't just some boring refresher. This is your guide to the procedures and, maybe more importantly, the mindset that makes sure you not only get the job done right, but you get home safe every single day. So let's start with the foundational rule, the one that governs everything else we do. This statement right here, it's not a suggestion. It's your right and it's your responsibility. Your company gives you the training, they give you the equipment, but when you're on site, you are the final authority on your own safety. If a situation feels wrong, you have the full authority to stop work, period. So here's our game plan for today. First, we'll start with the essential framework for every single job. Then we're going to dive into these specific hazards you'll face, everything from electricity to the environment. We'll also talk about the one hazard you bring with you to the site. And finally, we'll see how all this knowledge applies in a real-world scenario. Okay, let's get into it. Every single task, I don't care how routine it feels, has to begin with a plan. And in our field, that plan is the Job Safety Analysis, or JSA. You got to think of it as your first and most important line of defense against any kind of accident. Now, please, don't think of the JSA as just another form you have to fill out to check a box. It's an active, systematic process. Before any work starts, you use the JSA to actually stop and think, to identify potential hazards, to assess the risks, and to define the specific steps you're going to take to handle them. And this flowchart here, it illustrates the workflow perfectly. You start with hazard identification. Then you ask a simple question. Is the risk acceptable? If the answer is no, you assess how bad it could be, and you put preventative measures in place. Then you ask the question again. Only when that risk is down to an acceptable level do you actually start the project. And remember, if anything changes halfway through the job, you stop and you repeat the process. All right, now let's talk about one of the most pervasive and honestly one of the most misunderstood risks in cathodic protection, electrical hazards. Getting complacent in this area is just not an option. It can be fatal. You know, a lot of CP systems run on very low voltages, and that can give you a false sense of security. But dangerous AC voltages are often right there. especially when you're working near power lines or directly on rectifiers. We have to respect all levels of electricity. It starts so small. At just 1 milliamp, that's 1/1000th of an amp, the human body can start to feel a slight tingling sensation. That's it. That's the threshold of perception. Now let's bump that up just a tiny bit to a range of 6 to 25 milliamps. Suddenly, that shock becomes painful. And here's the really crucial part. This range is higher than what we call the let-go current. That means your muscles contract so tightly, so involuntarily, that you might not be able to physically let go of whatever it is that's shocking you. At 100 milliamps, we hit a lethal level. An amount of current that's small passing through your chest can cause what's called ventricular fibrillation. It's a rapid, chaotic quivering of the heart muscle. The heart just stops pumping blood, and death can happen in minutes. So, how does this actually apply in the real world? Well, it's all governed by Ohm's law. Current equals voltage divided by resistance. Let's use a really practical example. The average human body has a resistance of about 1,000 ohms. So if you touch a standard 120-volt AC source, well, 120 volts divided by 1,000 ohms gives you 120 milliamps of current. That is well within the fatal range we just talked about. That's why even standard voltage is so incredibly dangerous. This brings us to the single most effective procedure for preventing electrical accidents: lockout, tagout, or LOTO. Think of it like a seatbelt. Yeah, at first it might feel like a hassle, but it quickly becomes a non-negotiable habit that can and absolutely does save lives. It guarantees a circuit cannot be turned back on while you're working on it. And the rules of LOTO are absolute. First, the person who puts the lock and tag on is the only person who can take it off. No exceptions. Second, if you have a whole team working on the same piece of equipment, a group lockout device is mandatory. And third, your tag has to clearly state who you are, how to get a hold of you, and why that equipment is locked out. Now, what's really great here is that this slide shows that group scissor lock in action. Each technician puts their own personal lock on the device. What that means is the main switch physically cannot be flipped back on until every single worker has finished their job and taken off their own lock. It's a simple and totally foolproof system. All right, we've covered the electrical risks pretty thoroughly, but the field itself is full of other potential dangers. So let's shift our focus to the environmental and chemical hazards you're likely to run into. And the list is pretty extensive. We've got to be aware of explosive atmospheres, especially when we're around hydrocarbon pipelines. Induced AC from overhead power lines can energize a structure you thought was completely safe. Excavations, well, they carry the risk of collapse. And we're regularly working with hazardous materials, not to mention the dangerous gases that the CP process itself can create. Okay, let's break this down because it's really crucial. Our CP systems generate gases as byproducts. Over at the anode, you can get oxygen, sure, but you can also get toxic chlorine or carbon dioxide that can suffocate you, especially in deep ground beds. Meanwhile, at the cathode, you're getting hydrogen gas, and hydrogen is extremely flammable and highly explosive in an enclosed space. This is exactly why proper ventilation isn't optional. It's absolutely essential. So we've covered all the external hazards on the job site, but one of the biggest risks we face is one we actually bring with us every single day. Driving is a huge part of a CP technician's job, and you know what? Distracted driving is a silent killer. Now, distraction isn't just about texting while you drive. It's actually broken down into 3 types. You've got visual, which is taking your eyes off the road. You've got manual, taking your hands off the wheel. But the most dangerous, the most sneaky one is cognitive, taking your mind off the task of driving. You may have seen the invisible gorilla experiment. People are asked to count how many times a basketball was passed, and they focus so hard on that, they completely miss a person in a gorilla suit who walks right through the middle of the scene. It's a brilliant illustration that seeing is a function of your brain, not just your eyes. If your brain is tied up in a phone conversation, you can be looking right at a hazard and just not see it at all. So here's the crucial takeaway. Research shows that a driver on a hands-free call has a reaction time that is just as impaired as a drunk driver at the legal limit. Just let that sink in. Your hands are on the wheel, your eyes are on the road, but your brain is somewhere else. So the question you have to ask yourself is, what critical hazard are you failing to see? Okay, we've covered the principles, the hazards, the human factors, but knowledge is only powerful if you actually apply it. So let's put your understanding to the test with a real-world scenario. I want you to take a hard look at this photograph. Think of it as your final exam for today. Using everything we've just discussed, from excavation rules to just general situational awareness, your task is to identify every single safety violation you can spot. Is the excavation properly shored? Is there a safe way in and out? Where's the spoil pile located? Go ahead and pause this explainer right now and really analyze this. Look, ultimately, safety isn't just a chapter in a manual or some list of rules you have to memorize. It is a constant, active mindset that you have to bring to every single job site. Your most valuable tool isn't your multimeter, it's your knowledge and your commitment to using it. Because at the end of the day, your most important job is and always will be making it home safe.